Hey everyone, welcome back to the second half of our session on aquatic sciences. And I'm going to turn this over to Sylvia Lee from the United States EPA.
Thank you, Hilary. Can you hear me okay and see my title screen?
Sure can.
Wonderful. Well, first I'd like to say thank you to the session and workshop organizers for inviting me to give this talk. I'm happy to be here. I'm Sylvia Lee. I'm at the U.S. Environmental Protection Agency headquarters based in Washington, D.C. I am fortunate to work with some great colleagues there who helped develop this project. All of us pictured here are in a part of the EPA called the Center for Public Health and Environmental Assessment, and our group does research to support evidence-based decisions and actions to protect our environment, public health, and well-being. And I thought it was important to tell you about our group to provide some context for our approach for this particular project, where we're using information from the literature, data sets, and models, which are types of evidence that we can assess and synthesize to answer our research questions. And more broadly speaking, we're interested in KGML because we often work with both data-rich and data-poor sources of information, especially about ecological systems and field observational studies. And we'd like to know how we can put this information to work more efficiently. And it's important that we use information more efficiently so we can address widespread environmental problems like nutrient pollution in lakes. According to EPA's National Lakes Assessment, about 2 out of 5 lakes have excess total phosphorus concentrations. And this map here shows all the lakes that were sampled in the 2012 NLA, where the red points are lakes classified as most disturbed based on total phosphorus. And the NLA also found that these lakes in the red were more than twice as likely to have a degraded benthic macroinvertebrate community, which indicates that aquatic life is not well supported in these lakes. And a visible response that gets a lot of attention in response to excess nutrients in lakes is cyanobacteria blooms, which are increasing not just in the US, but around the world. This figure is from a study that used satellite imagery data from 71 lakes to determine bloom intensity based on the infrared signals, or to put it in really simplistic terms, how green the lake can get in a growing season. So this peak greenness has increased in many lakes, with the lakes indicated by the red triangles having the strongest increasing trend since the 1980s. And another study went back further in time using lake sediment records. This figure shows the concentration of cyanobacterial pigments in those sediments, which are stable for thousands of years once they are in the sediment and can be used as biomarkers of past algal biomass. The concentrations have increased rapidly over time, and this trend was best explained by nutrients and secondarily by temperature. There are some lakes where blooms continue to occur despite reductions in point and non-point source loading of nutrients. One example is Lake of the Woods. It's a large lake overlapping the border between northern Minnesota and Canada. I'm going to have several examples of lakes from Minnesota. And this lake used to receive phosphorus loading from paper mills and wastewater, but since the Clean Water Act, those sources have decreased, so the loading has decreased. Yet still, the lake turns green with algal blooms every summer. There's just so much phosphorus from past loading that's still in the lake and the lake sediments that the internal sources are feeding the blooms and remains a challenge for lake management. Better understanding of these internal loading and legacy phosphorus dynamics could help managers, especially if we could translate those phosphorus dynamics into estimates of recovery times. And what recovery time actually means will vary by lake and stakeholders involved, but having some estimate of when improvements to phosphorus concentrations could be detected given the internal phosphorus cycling could help managers set reasonable goals and stakeholder expectation. An example of that is another lake in Minnesota called Bartlett Lake, where information about recovery time helped the local community make decisions about how to spend their resources. So in the figures here are diatoms from the sediment record of Bartlett Lake. And because diatoms preserve water in lake sediments, we can infer based on the diatom species what the total phosphorus concentrations were like before any lake monitoring data became available. And you can see, even without being an expert diatomist, that there has certainly been a change in the community composition from the 1880s and to modern times. So in this figure, the y-axis is the year with the most recent year at the top, and going back further in time towards the bottom, similar to the age of the layers you'd encounter in a sediment core. And on the top is the x-axis with diatom inferred total phosphorus. The diatoms show that Bartlett Lake used to meet the state's standard in terms of total phosphorus concentration. And over time, there's been a gradual increase in abundance of diatoms, indicative of nutrient-enriched conditions. But point sources were removed in the 1970s, yet there has not really been much improvement in the diatoms because the diatoms are still responding to those phosphorus levels from internal sources. On the other hand, measured water quality, shown here in red, is slowly improving from over 120 micrograms per liter to currently around 40 micrograms per liter TP. And even though the recovery is pretty slow, phosphorus in the lake is continually being buried in the sediment layers. And based on the burial and the external load rate, that active pool of phosphorus will likely be depleted by around 2025, 2035, which will then be around 60 years of recovery time since removal of those point sources. And these estimates help the lake community decide that the best use of resources would actually be to have a bit more patience, as it seems that the lake is improving, although slowly. And to obtain this information, it was necessary to do a fairly extensive paleolimnology study and a phosphorus budget analysis for this single lake. However, that would not be feasible to do the same for a very large number of lakes. And that brings us to our research questions. The first question is a literature component. What are the important factors driving internal lake P cycling, and how do the relationships differ by lake ecosystem parameters? And what are the magnitude and consistency of these relationships? The second question is the modeling component. And we ask, if external phosphorus load into a lake is reduced by X%, how much time would it take for surface water TP concentrations to decrease by Y%? And these two components will inform each other, and together they'll be used to create an evidence base and model underlying some form of national map of recovery times for lakes across the US. So diving a little deeper into the literature component, this part is led by Kate Schofield. She developed this conceptual diagram that lays out the relationships among factors driving lake phosphorus cycling. And we found the paper by Jansen et al. Was helpful for developing the general framework to capture the relationships that are important for lake modeling. The framework consists of the four major components you see here in the diagram: the watershed, climate, hydrologic, and the lake ecosystem component. So from that more simple diagram, here's the full version that expands the components into individual parameters that we will search for in the literature. And just as an example, I highlighted a pathway that could be the focus of study in a paper where nutrients from the watershed combined with wind and lake water depth are factors that influence resuspension rate and phosphorus concentrations in the water column. Along with the conceptual diagram, we conducted a literature search using citation mapping and a more traditional Web of Science search. Citation mapping is a forwards and backwards search of the references in a selection of seed references, which are papers we thought would refer to or would be referenced by other papers that captured the relationships we included in our conceptual diagram. And so from the thousands of papers we found in our search, we screened the title and abstracts and narrowed down the pool of papers to a much more manageable number of 240 references. And I wanted to show you something here that I thought could be of interest to the workshop participants. We recently started using machine learning in our literature-based projects to more quickly find relevant papers with text mining software like a Swift Active Screener. And there is also an option to use seed references, which provides the knowledge base to give the machine a head start in learning which papers are relevant, much like what happens sort of conceptually in KGML. So after the screening process, we use a spreadsheet like this one to extract information from the literature. And if that looks a little overwhelming and a lot of work, that's because it is. It's a challenging task to distill the pieces of information we care about from each paper and documenting them in a form that makes it possible for a meta-analysis or some other synthesis in a transparent way, and can eventually be made accessible to many people rather than sitting in the computers of our team members. Most of the columns here in the spreadsheet relate back to the shapes in our conceptual diagram. We also capture information about the citation, the study design, data analysis and results, and conceptual information that can help us with interpreting the data. And it was also important to capture specific water body characteristics so that the information from the literature can inform our modeling effort. So the modeling component is led by Jim Carlton. These are the mechanistic model equations that Jim has adopted from a model described by Chopra and Kennelly that represents the lake system as having two compartments, the water column and the benthic layer. And earlier, we already saw a three-compartment model of Lake Mendota from Paul's introduction. I'll note here that because we'd like the model to be applicable to many lakes, and because many lakes have little or no data, our strategy right now is to use a relatively simple and generalizable model of lake phosphorus cycling, even though we do recognize that lakes are usually more complex than two compartments. So this relatively simple model starts with a steady case, steady state case, and then simulates a dynamic case, which I'll illustrate with an example. So this example is based on Xiaowei Lake, yet another lake from Minnesota. And Here we assume the influent and water concentrations are constant and in equilibrium with each other. We also have some basic data like water residence time, the water TP concentration, mean water depth, and the depth of the benthic layer. And we also have these coefficients, rate coefficients for the model, including settling rate, recycling rate, and the burial rate. Then we can simulate what happens to the water column total phosphorus after this equilibrium is perturbed by a sudden decrease in influent phosphorus. So let's say that a sudden decrease in phosphorus loading is by 80%. And we can also set a hypothetical target concentration that represents potential recovery of the lake as 10 micrograms per liter. The resulting output is the graph on the right here with TP on the y-axis and number of days along the x-axis. And for this example, it takes over 50,000 days or 137 years for this hypothetical recovery. So we can use the same calculations for many lakes, such as those from the Lagos NE dataset of lakes in the Northeast and Midwest US. Here we simulated the same 80% drop in influent TP for these lakes. And the colored circles are lakes that will reach our hypothetical target concentration from ranging from less than 1 year to over 150 years. And from this output, it's nice to see that many lakes could recover in less than about 30 years. And we also have lakes in the Northeast where they are indicated by green triangles. And these lakes have already reached that target concentration at time 0. And finally, you have some black diamond points here indicating lakes in more agricultural areas that mathematically will not reach the target concentration even with infinite time. So in this example, we simulated less of a drop, only 20% in influent TP, which of course results in more of these black diamonds. But perhaps it gives us a little bit of hope about these lakes in blue or purple, where even a 20% decrease in loading could improve the water quality in less than around 20 years. So in summary, nutrient pollution impairs many lakes, and internal loading remains a challenge, even when there are external load reduction efforts. We're using information from the literature and building a recovery time model to provide evidence for lake managers who may be able to use this to develop long-term plans. And we also want to make this data available widely. We're interested in learning about transfer learning, putting information to work in novel ways, and melding knowledge with machine learning, things that I'm not that familiar with. And just that this project is in its beginning phases. And thank you to Paul and Chris for their collaboration and providing insights. We welcome any feedback about this project and ideas about how KGML could enhance the research. So thank you, and I'll take questions if there's time.
Thanks, Sylvia. A couple of questions, probably just time for one. So I'll go with the one that was asked first. So this says, often our models approximate behavior for a population of lakes, but citizens might care more about, their specific lake. Is there a way to resolve these two views?
That's a big question. Yeah. We're trying to, with this project, get more at that population scale. but we do recognize that there are lots of variability among different lakes, and it is really important to consider where these more general models don't work as well for those specific lakes, and see how we can reconcile those. So I really don't have an answer for that question.
Yeah, it's a tough one. There's a few more, but we're gonna probably keep them till the end. So moving on to our next speaker, we have Charuleka Varadharajan from Lawrence Berkeley National Laboratory.
Hi, everyone. Thanks for the opportunity to present. This has been a really great session and really great talks. So I'm Charuleka Varadharajan, and I'm a research scientist in the Earth and Environmental Sciences area at Berkeley Lab. And my scientific expertise is in using data-driven methods for studying water resources. And I'm also involved in a number of other data science efforts with the US Department of Energy. I'm also a senior fellow at the Berkeley Institute of Data Sciences. So this talk today represents the work of several people. I've been really lucky to work with interdisciplinary teams. It's one of the perks of working in a national lab. And several of my co-authors are from the computing sciences area in the lab. And in particular, I want to acknowledge Julie Mueller and her postdocs, Ritik Sahu and Jangho Park, who really did much of the machine learning I'm going to be talking about today. Okay, so we're now collecting water data at an increasingly rapid pace, and machine learning is already transforming how we're making predictions in very complex systems such as watersheds and river basins. So in the past couple of years, the field of machine learning for aquatic science and hydrology has just exploded, and it's been a very exciting time. But water data today, as we've heard even earlier in this session, is really heterogeneous. We have multi-scale, multidisciplinary data, and we ideally want to make use of all data that's available to make predictions. But right now, our ability to use machine learning is limited when we're trying to diversify the types of data we're using, because our approaches to building models are brute force and inefficient, and kind of rely on trying out the kitchen sink approach, where we try everything out to achieve the best prediction accuracy. So if we want to make predictions at scale for a variety of problems, let's see, my clicks here are not working. Oops. Sorry about that. Okay, here we go. We need to think about reducing the computational and human overhead of building machine learning models without sacrificing accuracy. So today I'm going to talk about a few approaches we're using in 2 projects to address this challenge. So the first approach is to make mathematical improvements, which is what we're doing for a project that uses surrogate models combined with machine learning to predict groundwater levels in California. And this research was motivated by California's historic Sustainable Groundwater Management Act that requires local agencies to manage their groundwater sustainably and reduce undesirable impacts. So although some parts of the state, such as the Central Valley, have decades of work building multi-physics, multi-scale models, most other parts of California don't really have such models available, and typically the smaller agencies don't even have access to supercompute resources. So our research objective here was to build fast, efficient neural network-based models that could replace these computationally expensive, high-fidelity models to enable stakeholders to make timely decisions for groundwater management just on their laptops. So we started off with building deep learning models for some wells in Butte County, which is in Northern California. And we primarily chose this region because there was data available there. And by high resolution data, what we mean is actually daily data for groundwater and meteorology. And data availability turned out to be a pretty big challenge, because that wasn't the original region we would have targeted. We were originally eyeing something like the Salinas Basin, which is a high priority basin for the Sustainable Groundwater Management Act. But when we looked at the data there were only 2 data points a year. So we had to end up sort of switching. And by the time we actually ended up doing our analysis and the papers, actually the water withdrawals in Butte were high enough that it ended up becoming a high priority station for place for Sigma. So that's good for us, but very unfortunate for the residents of Butte County. So we considered 4 different popular neural network model choices here: the multi-layer perceptron, a convolutional neural network, and the recurrent neural network and its variant, the LSTM, which we thought would be good fits. The last two would be good fits for the modeling the temporal dynamics of the system. And each of these models had different hyperparameters to tune, and these hyperparameters determine the network's learning capacity and prediction capacity. So an important hyperparameter that we decided to include here to account for all the memory effects that happen in groundwater systems is the lag. And the lag here is the number of past observations that could influence the next day's values. So all in all, when we started to look at all the different hyperparameters and the ranges that we would want to consider, we realized that actually would end up with hundreds of thousands to millions of potential combinations to hand tune, which obviously was very computationally expensive. So Julie had developed previously a black box optimization approach that uses surrogate probabilistic models, which are namely radial basis functions and Gaussian process models, and converge to the ideal hyperparameter space much more quickly. And so we published this in a recent paper. And after we did develop that HPO approach, we also set up the models using 5 different input features that included for the training and for the hyperparameter optimization. So this was prior groundwater level measurements, temperature, precipitation, the nearest river discharge that was sort of supposed to be indicative of surface groundwater exchange, and the week of the year, which was supposed to capture the seasonality. And for the out-of-sample predictions, we only used the temperature and precip data to generate the predictions, and these were applied to single and multi-world scenarios. So we had a roughly 60-20-20 split for the training, the testing for the hyperparameter optimization, and then the out-of-sample prediction range. So the results here shows that surprisingly, it was actually, we didn't expect this, that the multi-layer perceptron actually outperformed all the other models. And this was about 4 to 6 layers here. And it was not just in terms of prediction error here, it was also in terms of computational expense. The multi-layer perceptron was about an order of magnitude less than the other models. And the key turned out to be this optimal selection of these hyperparameters. So in particular, for instance, these LSTMs and recurrent neural networks that we thought would do well actually couldn't capture a longer lag time. So they sort of stopped working when you had a lag of over 60 days. But these MLP and the convolutional neural network were able to account for about a year's worth of prior history, which it turns out to be really important in predicting groundwater system. So the other thing we realized is that we had to run several trials for this optimization because the results were slightly different depending on the random seed for the surrogate model. But so there's some stochasticity in the model itself, but overall we got pretty good predictions for all the different ensemble runs here for up to a year's worth. So we were just predicting the next day's value and using the prediction to keep predicting the future values. So this was up to a year out, we could predict fairly well. All right. Seems to be okay. Oops, that's going too much. All right. So here, I just want to oops, it's skipping a slide here. We actually also then did some follow-on work to explore the influence of differences in input features on the prediction outcomes, partly to see whether we could reduce the amount of time it took to train the model by dropping features, and also because we anticipate some data, such as the discharge, won't be available everywhere at the desired resolutions or periods of time monitored. So we had 9 different scenarios for 3 groundwater wells in Butte, Shasta, and Tehama counties, which are high, medium, and low sigma priority basins based on their water withdrawals here. And these are all the different scenarios that we ran. So the take-home message here is we had 2 major conclusions. The first is that the hydrological variables, which are primarily the precip and the discharge, are essential to obtain good predictions. If we drop both of them, such as this groundwater temperature scenario, the errors really shoot up. So that being said, it's also not necessary to use all the available data for all locations. So for example, discharge, which is the surface groundwater exchange, turned out to be less influential in the Butte region, where groundwater pumping dominates the water balance over everything. So this is all sort of jiving with our hydrological understanding of the system. So to sort of summarize this approach, there are two key messages here. First is that automated hyperparameter optimization approach dramatically increases the efficiency of building the models and allows us to explore a much larger parameter space without hand tuning everything. And also based on a parameter sensitivity test, it's promising that the obvious hydrological variable choice that we would go after turned out to be the most predictive. But it's also interesting that the choice of variables that gives the best performance varies by location, which is what we would intuitively expect based on our knowledge of hydrology. So this indicates that there's potential for just not using all the data that's available and throwing it at the model, but being clever about how we select some input features based on some hydrological understanding of the system. So I'm now going to switch gears and move to another project. So it's just taking a while to load. I'm not sure why. There we go. This is a project which is a DOE early career project, and it's mostly aspirational because it just got funded last September. But I'm going to be using a second approach that's really starting to think about how we can use knowledge-guided data science to do predictions of river water quality here. So the research objective is to understand the impacts of stream flow disturbances, both floods and droughts, to water quality here. And we'll be exploring whether we can infer knowledge about river corridor responses to disturbance as emergent properties that yield transferable insights using data-driven approaches as part of a framework to build better machine learning models. So this work is going to focus on 3 river corridors, the Delaware, and then the Colorado, as well as the Columbia rivers. These are important not just for the nation, but for the Department of Energy. And for this work, by water quality, I'm just referring to 3 different variables: temperature, dissolved oxygen, and conductivity, which are very important for water managers, but also from the machine learning perspective, they have high resolution data available. So the existing paradigm of using process-based models alone doesn't work to predict water quality across very large spatial scales, because we have really complex interactions that occur across space and time in watersheds. And the computational expense and the data that we would need to run such models just makes it very challenging to run. So here, there's this figure here that shows perhaps many different factors that really affect river water quality. And for each of these factors, we have many different data sets. So this can be a really big challenge. So what we're interested in doing is using machine learning, and particularly knowledge-guided machine learning, to think about how we can reduce this complexity for both short as well as long-term predictions. And so here, I'm going to cover 3 different science questions. Okay, so that are structured to add complexity. And sort of the science questions are the analogy of the shoe that Allison talked about. It's really a great analogy. We have to sort of tailor our models to be addressing these science questions. And so the first question is about how do disturbances impact water quality at a single location? So point to read scales at short and long time scales. The second starts to expand on the spatial scale and is focused on understanding the impacts downstream, along the river corridor and across river orders. And the third question then starts to broaden out to look at the landscape interactions with the rivers to determine how watershed properties can impact water quality. So ultimately, these questions seek to determine a resistance or resilience index of water quality as a function of disturbance and watershed properties. So my approach here is going to use a variety of data-driven methods for the predictions. And so recently, there's been actually a growing number of studies that look at these long-term water monitoring data sets, and these have included classical approaches such as regression to determine long-term trends, identifying patterns in hydrogeochemical behavior, in this case using Boltzmann machines or convolutional neural networks, methods to use information theory or causal inferences, as we heard even earlier today, to determine the drivers behind observed variables, and finally using some of the data in machine learning, which is already just beginning to show a lot of promise. But however, to date, most of these data-driven approaches have been used mostly in isolation and make use of a limited amount of data, relying on one-off products that are not updated with new data. So there seems to be this opportunity here to think about this more holistically, using some of these analytical methods to understand the underlying phenomena and the emergent patterns to help us build better machine learning models that are more scalable, interpretable, and transferable. So my approach is to derive some physical information by using different types of data analysis to answer the different science questions. So here, for example, the first science question here, I'm looking to tease out some emergent properties such as resistance, which is a change of the signal after the disturbance, or the resilience, which is the ability of the system to bounce back after a disturbance, and the lagged effects of prior events and disturbances on water quality. So I'll be doing this analysis on multiple timescales using wavelet multi-resolution analysis. And the hypothesis here is just that these emergent properties can help determine which machine learning model architecture, features, and hyperparameters to choose. So for example, if a system has a very long lag, it seems like based on sort of our prior work, we can't just choose an LSTM since that may not be able to represent a sequence that long. But the lag can also become the hyperparameter that we have in the model. So other questions that we can ask are whether we need a single model for an entire basin or for all rivers, or whether we should have different models based on some inherent grouping that's either spatial by watersheds or temporal by some stochastic regimes. The idea here is to then, sorry, it's taking a moment to load here. Is to build this data-driven framework that will contain an analytical module where the core elements are the outcomes of an analysis done for a particular science question, and ultimately build up to the machine learning model for the prediction. So for example, here we're going to start with that same deep learning algorithm with the hyperparameter optimization for the point scale science question to predict at the point scale what the water quality is. But the framework is also going to have a data integration component here that pulls data from various sources on demand to make the data analysis repeatable, reproducible, and not based on one-off products. And just sort of given the diversity of data that's available and potentially usable in this research, this becomes really important to do because we need to try to make use of as much data as we have to arrive at the right results. So for this purpose, we're building a data integration piece of the framework as a base capability that allows us to pull in new data on demand. This is a software called Basin 3D that connects to diverse data sources and transforms data and metadata into a standardized format. So the software has two modes. The first is a Django-based tool that supports web services and portals for data discovery and visualization. We've done that for another project already. But for this early career work, we had extended the software to become an installable Python module that can flexibly connect to different data sources and be used for data analysis within a Jupyter notebook. So this harmonizes all the data into sort of a single data frame for the analysis, which seems to be truly unique because this then starts to deal with the problem of bringing data into a common format, which is just really a major pain point for building machine learning models. So to summarize here, what we're doing is to look ahead and move towards using a cascading series of data analysis to answer science questions or test hypotheses that can then provide us a more structured way of incorporating our domain knowledge into the machine learning. And ideally, that'll help us improve both the model accuracy as well as the time it takes to build these models. We're also building this software that will provide long-lasting capabilities to synthesize data into a uniform format and incorporate new data as they become available and reduce our reliance on these one-off data products. I just also, since we had a lot of questions earlier about extremes, I want to say that dealing with extremes has a lot of challenges. There's more missing data because there's less, there's more tendency for sensors to fail, and traditional error minimization approaches don't work. We have skewed distributions, etc. So to conclude, I want to just say that the key take-home message is that knowledge-guided machine learning is this unicorn space shown in this Venn diagram. It's the confluence of math, computer science, and domain science. So in our projects, what we've done is to try to match up mathematical advances such as the hyperparameter optimization with some computational advances such as cyber infrastructure for model data integration and data pre-processing, with the domain analysis to help inform the choice of model architecture and parameters. I'd also like to call out in general, we need more benchmark data to compare our models, and I would love to see some movement there to start to generate more fair data, which are machine-readable data products we can use for the machine learning. And as we've heard from many of the great talks in this workshop, the important thing is to enable the collaborations by ensuring that all these partners across these disciplines are recognized and credited for moving this field forward. So with that, I just want to thank everybody for listening. I also happen to be looking for a postdoc, so please contact me if you're interested. Yeah, and these are everybody I want to acknowledge, including my funding.
Charu, thank you. That was great. And another fantastic postdoc opportunity. Question for you. In groundwater level prediction, can you factor groundwater pumping rates as a predictor?
We would love to. There's no data on it. Unfortunately, California doesn't monitor pumping. We've tried a lot of different ways to estimate proxies for pumping, and it's just really hard.
You'd think if anywhere would monitor pumping, it would be California, but I think maybe in the panel, we'll get back to what types of data we should be monitoring. Well, thank you very much. That was great. We're going to move on to our last talk. Next up is Xiaowei from University of Pittsburgh.
Hello, everyone. This is Xiaowei. So I just graduated from the University of Minnesota last month from Vipin's group and joined the University of Pittsburgh as assistant professor in computer science. So very happy to have this chance to give this talk in our HDR KGML workshop. And my talk today is about integrating physics into machine learning for monitoring scientific systems. So in these recent years, we have seen this machine learning and data mining, these techniques have found a lot of success in different commercial applications, like in computer vision, natural language processing, and so on. So that's why there's a growing interest in using these machine learning techniques in scientific domains as well. But actually, we have seen many failure examples for directly applying these machine learning techniques as black box in these scientific problems. For example, the very famous Google flu trend prediction. And also in the domain of climate and biochemistry, there are many failure examples. So we may want to ask, why do these black box machine learning methods fail in our scientific problems? And here we summarize a few major reasons. The first one is usually these scientific problems, they are very complex, so they involve a large number of physical variables, and the relationship between these variables are non-stationary, so that means the relationship can change over space and over time. It's very hard for machine learning models to capture such kind of complex relationship solely from data, and especially if we have access to only very limited amount of observation data. So that makes the training process even more challenging. And also, most existing machine learning models, they focus on mining the statistical relationship from our available observation data. So they are not aware of the underlying physical processes. So in that case, it's possible that these machine learning models can produce some results that are inconsistent to our known physical relationships. For example, they may not conserve energy or may not conserve mass. And that's why these many domain scientists, they may not fully trust these kind of black box machine learning methods. And also, they can only discover the relationship from our available training data. So it's very likely that these learned patterns from available training data may not generalize to scenarios that look very different with our training data. So traditionally in scientific domains, the domain scientists commonly build different types of physics-based models. And these physics-based models are mostly developed using our current knowledge of the scientific theory. But there are also several well-known limitations of these physics-based models. For example, their representation of physics is usually incomplete, either because some physical processes are still not fully understood by domain scientists, or they're just too complex to be directly modeled. And also calibrating these physics-based models can also be very time-consuming. And on the other hand, machine learning models, we know they're very powerful and they can automatically extract different types of complex relationship automatically from data. But training such kind of machine learning models usually require a large amount of labeled data. And also, as we mentioned, they can produce some results that are inconsistent to our known physical relationships. And that's why we want to combine these two types of models together, and we call this hybrid framework as physics-guided machine learning. And the idea here is that we want to leverage both the power of machine learning and also the physical knowledge encoded by existing physics-based models. And this kind of hybrid framework actually can be widely applied to many different domains because so far in these scientific domains, people are still heavily relying on different types of physics-based models. And there's still a large gap for using these physics-based models to simulate true phenomenon. That means there's still a lot of space to make improvement. And my talk today is going to be focused on using this hybrid framework, physics-guided machine learning, for modeling physical systems with interacting processes. And I want to use the example of predicting water temperature and stream flow in river networks. And this study is very important because an accurate prediction of in river networks actually can provide many useful insights about the like aquatic ecosystems and the water quality and so on. And in these river networks, there can be multiple river segments. So they can have quite different dynamic patterns because they have different geometric structure and also they have different climate conditions. But these different river segments, they can also frequently interact with each other. So like the water evacuated from upstreams can directly impact the water downstream. And the most challenging part is that usually in a river network, there are only a few river segments that are frequently monitored. So that means we usually have limited training data for training advanced type of machine learning models. And so from a machine learning perspective, here we list 3 major challenges involved in this project. And then we also provide our solution for each one of them. So the first challenge is that, as we mentioned, like most river segments are poorly observed, or they are completely unobserved. So in this way, it's impossible for us to build individual machine learning or purely data-driven models for each river segment separately. And so that's why we will, in this work, we will build a global machine learning model for the entire river network or the entire system. And the second challenge is traditional machine learning models cannot simultaneously capture the interactions between different processes or between different river segments, and at the same time capture the temporal dynamics within each process. And to solve this problem, we will propose a new machine learning architecture called recurrent graph neural nets. And the last challenge is that we know that the power of these deep learning models or these neural network models mainly comes from their ability to extract these hidden representation or hidden variables in these middle layers. But these learned or extracted hidden variables can become less meaningful if we only train this model using limited observation data. So to solve this problem, we will propose a new learning strategy. Basically, we want to transfer the knowledge from existing physics-based models to guide the learning of these hidden variable or hidden representation. And we will cover these challenges and our solutions one by one. So we start with introducing the basic structure of the recurrent neural net. So this type of machine learning model is very widely used in different machine learning applications. And the power of this model mainly comes from their use of these RSTM cell or the long short-term memory cells which can be used as memory to preserve all the information from the past history. And as we mentioned, like in our work, many river segments are poorly observed. So we cannot build individual models so that we will build a global machine learning model for the entire river networks. So here, for example, we consider this very small river networks with 3 different river segments, A, B, and I. So in this case, the global machine learning model or the global recurrent neural network model means we train this global recurrent neural net using all the available data set, all the available observation data from all these 3 river segments. So we combine the available observations from the 3 river segments together to train this recurrent neural nets. And after we train this model, we can apply the model to each river segment to generate predictions, the meaning of global machine learning model. But as we mentioned, like this recurrent neural network can capture this temporal dynamics, but it cannot model the interactions between different river segments. Like in this case, it cannot capture the influence from upstream A and B to the downstream segment I. So that's why we propose this new architecture called recurrent graph neural nets, where we introduce a graph structure for this to represent this different river segments in this network. So here in this graph, each node represents a river segment in this network. And we add an edge for between each segment I to segment J if segment I is upstream of segment J. And the weight or the affinity level between each pair of river segments is measured by this their stream distance between this pair of river segments. And remember, this is the structure of the recurrent neural nets. And for example, here if we wanna model this downstream segment I, so we also wanna incorporate the influence from its upstream segment A and segment B. So what we do is, when we calculate the RSTM cell for the downstream segment I, we also incorporate some hidden states or hidden variables HA and HB from upstreams. So basically from HA and HB, we first transform it into QA and QB. Then we pass this information from QA and QB to the RSTM cell structure at downstream segment I. So that when we calculate this RSTM cell, we can gather sufficient information. Basically, we can gather or receive the influence from its upstream segment A and segment B. But now that we propose this structure, but these hidden variables, they are automatically learned if we directly train this machine learning model using an end-to-end fashion from observation data. So we don't exactly know what kind of information is propagated from upstream to downstream segments. And then if we train this model directly using very limited and less representative training data, it's very likely that these hidden variables QA and QB can become less meaningful. So to solve this problem, we propose to transfer the knowledge from physics-based models to guide the learning of these hidden variables so that we can enforce some very general physical relationship amongst different river segments. So we will use an example of modeling the water temperature in river networks. So according to the energy conservation law, for each river segment, the temperature change is dependent on the difference between incoming and outgoing energy fluxes, and plus an additional term of net heat advected from upstream to downstream segments. So basically this term HADV, this net heat advected, this term is the influence from upstream to downstream segments, and it's the value that we want to model in our graph neural nets. And this term HADV can be calculated as a function of a set of intermediate physical variables. So these include like the stream flow, like the water temperature of the upstream segments. And actually, this is very intuitive because we can imagine like when the water merge from upstream to downstream segments, then the amount of water that flow into the downstream segments and also its water temperature can directly impact the change of water temperature at downstream segments. And to model this relationship, we propose a new loss function. Basically, this loss function is used to ensure or guarantee that we can extract this set of intermediate physical variables from our hidden variables QA and QB. So here we represent these intermediate physical variables using the symbol SA and SB. And then by minimizing this loss function, we can guarantee that we can extract this SA and SB from our previous hidden variables QA and QB. So if we can do this, then we can make sure that these hidden variables QA and QB, they indeed contain sufficient information to represent these intermediate physical variables. And then once these hidden variables are passed to the downstream segment, this RSTM cell, then this RSTM cell can gather sufficient information to estimate this term HADV, which is basically the impact from upstream to downstream segments. And in our implementation, this set of intermediate physical variables can be simulated by running a physics-based model. And then we notice that the calculation of this loss function is totally independent of true observations. So that means we can minimize this loss function in a separate pre-training stage. So basically the pre-training is to update these weight parameters along these red color connections. And then once we finish pre-training this model structure, we can just fine tune it using limited amount of true observation data. And here we show some results for modeling water temperature and stream flow in a river network. So this is in Delaware River Basin, but it's a subset with a total of 42 different river segments. And our training data are selected from this 24-year period from 1980 to 2004, and we test in the following 12 years. And so here, these numbers are prediction RMSE, so the lower the better. And we can see that our method, the last two rows are our proposed method. RGRN basically is a recurrent graph neural net, and the last row is the method after using the knowledge transfer or the pre-training. And we can see our proposed method always gives us a better performance compared with baselines, and that's because we use this kind of graph structure to model the interactions between different river segments. And we also trying to randomly remove some training data. Basically, we randomly select 0, 1% of data or 2% of data, basically to evaluate the performance of each method to see whether it can still get a good performance even with access to a very limited amount of training data. And we can see all these methods get worse performance when we reduce the training data. But our method can still get a reasonable performance even with just 0, 1% of training data. And the reason is because we do the pre-training using large amount of simulation data, because we can always generate simulation data for every single date and for every river segments. So after pre-train the model using a large number of simulation data, then we can get a good initialized point for this machine learning model, and then it can be fine-tuned using very few amount of true observation data. And here we show the distribution of prediction error across different river segments in this river networks. And here we show the left side is our proposed recurrent graph neural net, and the right side is the standard recurrent neural net. And here the darker blue color means the better performance, and the darker red color means worse performance. So in general, we can see for most river segments, we have a little bit darker color, darker blue color. That means we get better performance. And especially for certain river segments, we can see our method get much better performance. For example, this segment in this dashed circle. And the reason is because in this segment, we have very limited amount of training data. So in the first 24 years, but we have plentiful of the testing data. And the performance is bad in RNN because if we don't have sufficient training data for this segment, then it cannot capture the local patterns of this river segment. But for our method, even if we don't have training data on this segment, but we can still use this information propagated from its neighbors in the graph. So we can still learn something useful to help improve our prediction on this river segment. And to better verify this assumption, we do this following test. Basically, we select 5 river segments in our river network where we have sufficient training data for both temperature and stream flow. And then we intentionally hide the training data for either temperature or stream flow. And then we measure the performance before and after we remove such training data. So here we show the performance before and after we remove the training data. And in the middle, we show the increase of prediction error after we remove the data. And we can see that our proposed method always gives us the lowest increase of RMSE after we remove the data. So that means our method can still be effective even for modeling those river segments that are completely unobserved. And finally, we do the generalization test. Basically, the idea is that we want to train and test the model using data from different distribution. So for example, like for water temperature, we will train the model using data only from colder seasons, and then we test in summer. And for stream flow, we will train the model using data only from those high flow streams, and then we test on data from low flow streams. So the second column here is basically the baseline, and we show this generalization performance in the first column. So we can see like some methods like ANN, the standard neural net, and the standard recurrent neural net can give us rather high performance in this generalization test. That means this method, the learned patterns from this high flow cannot generalize to low flow streams at all. But our method, the last row, after we do the knowledge transfer through pre-training, can always give us the lowest, much lower prediction error. And the reason is because after we do this, by doing this knowledge transfer from existing physics-based models, we actually enforce our machine learning model to learn some general physical relationship that always hold in different scenarios. And that's why it can be better generalized to different scenarios. And to conclude this talk, we propose a new model architecture, and also we propose a new pre-training strategy to transfer knowledge from existing physics-based models. And we have shown this method is quite effective for modeling river networks. And in future, we would like to pursue several interesting directions. For example, we want to further extend the current framework to see whether we can quantify the uncertainty level of machine learning models, so we know that, like, in what kind of situation can machine learning be better used to replace existing physics-based models? And maybe for some other special situations, the physics-based models is quite robust, so we can still keep using original physics-based models. And also, we want to provide some theories to see if we can identify the limitations of existing physics-based and machine learning-based models. And that's all for my talk. Thank you. Any questions?
Thanks, Xiaowei. Yeah, so there's a few questions for you. So the first one is, how do you guess how many hidden variables there are?
Yeah, so I think, so for my test, like what I do is I first implement this method using a purely simulation data. So the simulation data is available on every single data, every segment. So on the simulation data, I try to tune those hyperparameters, and then I fix it, and then I use the same setting on the real true observations.
Next question. The physics model for heat transfer shown is missing exchange with the atmosphere in the stream bed. Are those terms really missing from the model?
Oops. Let me share my screen. Okay. Right. So I think so just confirm that I understood the question correctly. So you mean in this equation I ignore some physical terms and whether that's included in my machine learning model? Is that right?
I think so. Yeah. If there's exchange with the atmosphere, heat transfer with the atmosphere and heat transfer with the stream bed.
Yeah, I think so I think we ignore several minor terms in this equation, but I think for the first term is basically like the incoming energy fluxes, like the solar radiation and these things, and outgoing is like evaporation and these things. And the third one is the influence from the or the advected heat from the upstreams. But we ignore some minor terms, and we just found it's not. The performance won't change too much by ignoring those minor terms in this equation.
All right, I'll try and do two more questions quickly. One is, how do you define the river segments?
Okay. Yeah, I think I get this data set from our collaborators. So I think they have their way to segment this river into different segments based on their length and certain parameters. I'm not fully familiar with that process, but I can provide more details later.
And this is the USGS.
Right.
Yeah. All right. Last question. How scalable is this approach? PRMRS SN temp models do not exist everywhere, and they are expensive to build.
Right. So I think running these models can be very time consuming, especially like if we want to calibrate these models, it can be even, it just takes weeks of time. So what we do is, I think, so we're trying to, like here, so here is where we use the simulation from this PRMS as intent model. So we don't calibrate this model. We just use a like generic version of this model to generate simulations. So our assumption is that even if the simulations are not perfect for these river segments or for these river networks, but still by training from these simulations from a generic model, we can still learn some useful patterns. I think if we just do the predictions from or just do the simulation using a generic model, that should be fine. But if we want to calibrate the model to make it customized to each river segment, to each river networks, then it takes a lot of time, according to my knowledge about this model.
Great, thanks, Xiaowei. So now we have approximately 17 minutes for a sort of general panel for all of the speakers. So for those speakers who are willing to, it'd be great to have you come back with your video and audio. I've tried to sort of summarize some of the questions that have been asked already on Slido, but if anyone who's listening sort of has general questions for all the panelists, feel free to throw them in Slido. But one question that's sort of come up in different ways for different speakers is thinking about observational or training data for these models. And you all work in sort of different niches across the field of aquatic sciences. And I'm curious from everyone, what would you say is limiting the implementation of these models in terms of having that training data?
I would just say, and I think Charu will probably add to this, it's just like there's harmonizing data. There's a lot of data out there, but harmonizing and getting it together in a trustable, analysis-ready data set is just a vast, horrendous. That was the last slide I got to, which is basically like harmonization sucks. And that's why we don't have this stuff as much. So, Aquasat uses Google Earth Engine and JavaScript and all that, but it was probably like 6 months of harmonizing the water quality data and 2 or 3 months of learning Earth Engine and implementing all that. The hard part was the harmonizing. So I think getting, at least on the water quality side, getting everything in the same place with the same annotation and the same all that stuff is just really hard. And I think Charu probably has more to add.
Yeah, we had this discussion. I mean, I absolutely agree that harmonization is a pretty big challenge, and that's partly why I didn't even, I'm collaborating with folks from the USGS who've done all that hard work and just using their data set. It's partly why I made that call for fair data, because there is data out there. It's not curated in a way that we can use as benchmark data sets. The Aquasat, and there's camels, and there's all these things starting to emerge that I'm seeing becoming very popular de facto benchmarks. But I think we need to be thinking about, how do we fund some of these efforts just to build these benchmark data sets that we need. So like the ImageNet sort of equivalents, the MNISTs for our aquatic sciences. I also want to say that, in general, like for instance, streams and rivers, they're like you've heard all throughout today, they're not monitored at the frequency we really want. So there's a very small fraction of streams that have been monitored. And so, in what we've been thinking about is in some of our projects, this concept of co-design, which I didn't talk about today, but how can we use these models to inform where the observations are being collected? And there are opportunities, especially with the USGS funding some next generational water observing networks, to see whether we can start to use some of these models, like in the Delaware Basin, to inform perhaps where the next measurement should be going. So that's another thought. We should be talking with the field folks to be seeing how we can synergize with them to collect the data that can help the models.
Great. I don't know if anyone else has any other thoughts on that topic. Robert, this question came up during your talk, but it was thinking about scaling up, and how do you scale up when, or in scaling up, does that bias of regionality cause problems when you're training on sort of temperate lakes? How do you scale up to kind of other systems? And that might be thinking about observational data and it being biased to certain aquatic systems.
Yeah, that's a good point. I mean, we didn't do the scaling up yet, so this is a problem for the future me. But I mean, the model is really simplified that we are currently using. So we hope, because we have all these parameters and they are more black boxes. So now we're doing all this data exploration using machine learning to understand which equations we have to include that make the model more robust for scaling up. But this could potentially be a problem if we only build models for the US Midwest and then we want to apply them for some other place. Then yeah, there could be problems, but we really hope that the machine learning can pick up these signals that we are currently neglecting.
If I could jump in for a second, I think it relates very much to the previous question, which is how do we prioritize the kinds of ecosystems for which we get data? And so far the prioritization, as Matt pointed out, is systems that we're monitoring for water quality, purposes. But maybe we should be emphasizing big gradients that we feel are important to understand sort of underlying process in the system. And and I agree, probably a lot of those data are out there, but the harmonization and munging effort required to make those data usable is sort of insurmountable without either help from federal agencies who already kind of have this, at least in part, on their plate, although water quality kind of falls between the cracks, actually, of a lot of federal agencies, or other funding efforts.
Yeah, so getting back to sort of scaling up, and Jared, in your talk on transfer learning, one of the questions that came up was, is there potential for these models to be overfit to sort of the training data set?
Yeah, so that is possible, but given how the meta learning is constructed, you can think that some of that is taken into account just because your training data for the meta model is based on transfer, and if it's overfit, those models won't transfer well during the training set.
So it seems like a pretty good approach.
Yeah, I think one idea we can explore is like I think Jared previously mentioned this, even if it overfits somehow, but then if we only use this meta transfer learning model, the base model as a base model when we adapt to a new place, but then we allow some fine tuning using a few amount of true observations from another basins and other systems, and then it's possible to just adjust the model to better fit the new scenario. And that's, I think, another thought. Yeah.
Also, model agnostic meta learning is a whole framework that kind of does that, and it tries to specifically find models that are adaptable to a lot of systems, and that's the goal of it. So that's another way of doing that.
So one thing that I'm not sure if it came up in anyone's talks, but was sort of I was thinking about was this switch from sort of traditional just process modeling to machine learning. And with process models, there can be a huge time investment in calibrating them to a specific site. And that calibration effort can stretch on for months to years. And so while it seems sometimes simple to implement a process model, it can be really time consuming and difficult. And so how do you view using machine learning models actually as sort of a time-saving application, rather, on top of being potentially more accurate and more transferable?
Yeah, I think machine learning has a lot of promise in this use, because not just in aquatic science, but also in some other domains. Because we always want to generate data at very high resolution, but running these physics-based or process-based models at this higher resolution is always very time-consuming. So that's why people usually do a lot of approximation to generate data or simulate data at much coarser resolution. But using machine learning model definitely can provide a lot of promise there. I find there, I think Jared when Jared do this survey paper, I think we found several existing research that people just generate a few amount of simulation data at higher resolution, and then they train a machine learning model and use that machine learning model as a surrogate model to replace physics-based models to generate high resolution data. And that's basically considering the time cost of directly running this process-based model. I think there's a lot of promise there in this area.
Yeah, I want to add to that, sort of saying that we are taking a similar approach with our California groundwater example and trying to simulate a hydrous model. I think that was part of our motivation for even building a machine learning model like this, kind of physics-based model, even if it exists, like the Central Valley models have been like decades of investment to get them running and working right, and the dynamics are constantly changing, so that's a challenge. And within a year, actually, we were able to, if the data are available, within a year, we were able to get a machine learning model up and running and actually doing predictions out to a year, which is pretty fantastic in terms of how we could actually get there so soon. So that's, I do think it shows a lot of promise. The challenge is whether we have the data.
Any other comments on the time investment of machine learning that you've all spent lots of time on?
Oh, did I interrupt somebody? No, okay. So this is more about the time investment for the numerical simulation. And just emphasizing your point, Hilary, that sometimes it'll take a graduate student really a full year to get a hydrodynamic water quality simulation running for one system. And, I think there's a good argument to be made for the student learning a lot, in the process of getting that up and running. But on the other hand, they're way over parameterized. And so it does leave you wondering how much of the underlying process you really are learning about. And, it's sort of a general question in my head for those, especially, who've had a more experience in the KGML world. What are the trade-offs between using a fairly complicated simulation model as your process input, versus one or two or three very simple models that are really easy to spin up to help you? And I don't know if there's an answer among the group. But.
Definitely trade-offs.
Yeah.
All right, so in our last 5 minutes, this is a question that I'm hoping everyone might have an answer to, but I'm guessing we have a handful of students out there listening who are interested in this field and sort of trying to get into it. And this is an emerging frontier in aquatic sciences, and it's not something that students are traditionally trained in. And there's few sort of course opportunities to learn about machine learning in domain sciences. And so, if you're a student stuck at home for the next semester and have some spare time, what would you recommend dabbling in terms of learning some new tools and skill sets that might help you out? And you don't have to be a student stuck at home. You can be a emeritus professor stuck at home.
I would just say, like, find a play example. Like, that's low. It's not necessarily your dissertation, but it's just something that you can spin up to try to learn. I mean, whether it's Python, it's probably Python if you're going to be doing any of the sort of more neural net stuff. Just finding a way to play around and find any of these data sets. Charu mentioned camels. That's a good one if you want to predict discharge. Just some data set that's already curated and is just ready to go, and you can just start playing around with learning these things. I think it starts. I'm trying to learn some of this LSTM modeling, and that's where I'm going to start. So I think just making sure it's play and maybe not embedded in your work just yet if you're starting out, because it takes a long time to sort of get there.
Yeah, I want to add that I think the platforms these days are so, computational platforms are really easy. Starting to work with TensorFlow or PyTorch, whichever is your favorite one. It's really easy to get spun up with a few lines of code. It didn't used to be the same way 10 years ago. You have to do everything yourself. Here, with a few lines of code, you can get these models running. I think it's the subject matter sort of expertise and really thinking about how you construct the problem, what kinds of data you want to use. This is why going with a pre-existing data set is kind of fun. And I'd say, there's a lot of work, especially that's starting to emerge, which has the data and codes that are already being published online. So that's a good place to sort of try to replicate something to just get started.
And I think for people who develop this method, like for ourselves, I strongly suggest that if possible that we can share, or if we can release all these codes and data sets to the public, because like if I just read the papers, I may easily get confused with like how to implement the physics-based laws without knowing details about these things in Python. And I think that would be very helpful for people who just want to get started on this project.
I see everyone nodding, Xiaowei. I think we all learn well from reading other people's code, so thank you in advance.
Yeah, just to add to that, I think this came up a couple times too, that it not only is it the code, but also the hyperparameters that go into many of these models require some thought and experimentation. So including methods that we used to reach the choices that we made could be useful.
Great. Well, if there's no other closing comments from our panelists, I just want to thank you all for speaking. That was a really enlightening group of talks. This is recorded, so hopefully it will be available for everyone to watch again when you want to go back and remember the details. Just want to also say that this was day one of our KGML workshop. So there's a full day tomorrow, starting with hydrology at 9:30 a.m. Central, and weather and climate in the afternoon. And all those talks are available. The set of talks is available on the website. So we hope to see you there tomorrow as well. So thanks, everyone.
Thanks, everybody.